Okay, so one of the applications of intervals that we'll use in engineering is for the concept of work. And work is defined as the energy required to do a task. And since it is an amount of energy, we generally measure that in joules and when we're talking about SI, or an equivalent measure in English units. And if we remember from unit conversions in the past, we know that 1 joule is 1 Newton times a meter, which helps leads us to another definition of how we get to work, which is a force acting through a distance as a particular type of work. And so the force being in newtons times the distance, which would be in meters, would give us Newton meters, which would put us in joules. So this is just a particular example. Of course, if it were linear relationship, if the force was constant and we were just pushing across a distance, we could just simply say that work equals force times distance, or times our change in distance. One of the things being involved with that is that with work, it is what they call a path-dependent function, which is another way of saying that our route matters how we get there. One of the things you talk about if we know something about physics, we know that if we move from an object from here and we move it vertically, that the potential energy is changed because we have moved it through gravity to get there. And so the work is the energy it took us to move the pencil from here up to here. So we exerted a certain amount of force through a certain amount of distance. Now, no matter how I get there, there's a difference in potential energy of getting there. But the actual work that I have to do would change depending on whether I decided to, what other motions I might decide to do in between there. So we can actually end up expending more work than just the difference between the two places. So as I said, we're not going to work with potential energy right now. That would be an example of a function that's path independent in that it doesn't matter what route I take to get there, the difference in energy there is the same, whereas work it does. And so as we talked about, work is, the way we're going to think about it right now is as this force acting through a distance. And of course we're thinking about integral, so if we think of force as a function through a distance, through distance added in infinitesimal difference, so we go from it should be delta x. We go from a delta x to a dx. Clean that up a little bit for you. And then the function we can get for work is that work is the integral from where we start, which we would call the origin, d, or 0, to our end distance, d, of our force function, dx. And so that looks like an integral, which is the things we're wanting to talk about. So now let's look at some specific examples and see what it would take to get through 1 meter. So we've got some examples here on our worksheet. So it says we're pushing a block at a distance d meters. The force N that's applied to the block, its starting point, is denoted by F of x. We let W denote the work of the block. And so we see the amount of force we're applying changes as we go through the distance. This could be because of whatever ramp we're pushing it against or whatever the case. But we're having to apply a different amount of force depending on where we're at in our path based on these 3 functions. All right, so let's try that. Okay, so again, what we're trying to do here is determine the work for a distance of 1 meter when we have these different functions. So the first one is a polynomial. So we'll start with that. So I'll take my original equation, plug in the things that I know from it. I'm going from 0 to 1 meter. I've got my function here, dx. Now we want to do the antiderivative. And so each term, remember, to get x squared would become x cubed, I'd divide by 3. X would become x squared, I'd divide by 2. And 4, I would get an x on there. And remember, I can ignore the plus c term because I'm doing a definite interval. I've got points I'm going in between, so I don't need to add the plus c because it would just cancel out anyway. Plug in my values. When I plug in 1, I just get 2/3 times 1 cubed, 3/2 times 1 squared, plus 4. When I plug in 0, they all these are going to go to 0, so I can just ignore that part. Then I just have to kind of add my fractions together. So to simplify that, get a common denominator of 6. So 2/3 is 4 out of 6, 3/2 is 9 out of 6, 4 is 24 out of 6. Add all those together, I get 37/6 or 6.17. All right. And again, units would be either Newton times meter or joules. And so we use joules here for that one. All right, so that's the first example. Part B asks us to use the function f of x is 2 sine of pi over 2 times x plus 3 cosine times pi over 2x. And we would want to set that into our work function, which would look like that. And then we would want to do the integration, do the antiderivative. So when we do the antiderivative of sine is negative cosine we multiply by the inverse of this. So if our coefficient here is pi over 2, we're going to multiply by 2 over pi outside. With cosine, the antiderivative of cosine is sine. Again, when we would multiply by the inverse of this coefficient, which is 2 over pi. So there we have our 3 antiderivatives. And then we just need to plug in our values at 0 and 1 to get a numeric value. So we would plug in. So we simplify the coefficient first. We'd make that 4 over pi. We're plugging in 1, so we just get pi over 2. And then we get 6 over pi. We plug in 1, we get pi over 2. So for the first half, we can group that off if we want. When we plug in 1, we get those expressions. And when we plug in 0, we get 4 over pi times cosine is 0, and 6 over pi times sine is 0. Again, the inside has x in there, so it just goes to 0. Nice thing is because we have these values of pi over 2 and 0, that some of these terms are going to go away. So when we have that, since cosine of pi over 2 goes to 0, sine of pi over 2 goes to 1, so we just end up with the 6 over pi term from the first half. And from the second half, the cosine term goes to 1, and the sine term goes to 0. So we just end up with the cosine term for that. So we really just end up with 6 over pi minus 4 over pi, which is 2 over pi, which is an exact answer. Of course, in engineering, we generally want to get it out as a decimal because we can't just turn into our bosses whatever 4 over pi is. And actually, I've made an error, so we're going to have to go back and fix this. The error that I've made is that way up here, when I did the inverse of cosine, or I'm sorry, when I did the inverse of sine, we should have gotten negative 1 over omega times the cosine. So there should have been a negative here, which means that should have been negative 4 over pi. That should be negative 4 over pi. Which means when I did this part, that 1, it's actually going to be minus negative 4 over pi. So, which makes this 10 over pi instead of 2 over pi. Again, that's why it's very important to keep up with your signs, and it can be very confusing with using when you do derivatives and integration with sine and cosine. Remembering which one is the positive, which one's the negative, and that's why I should always keep my sheet with me. Okay, so instead we get 10 over pi once we corrected for the negative signs here, and then doing that as a decimal, we would get 3.18 joules. So our answer does turn out to be a positive number, which is important. But yeah, we have a negative sign that we lost in the middle there. That was my mistake. Sorry about that. So yeah, make sure when you do the antiderivative of sine, you get a negative cosine, which one we carry through. So our third example of work is the function 4e to the pi x. We would do the same thing that we've been doing, which is to set up our equation. work is integral from 0 to 1, because we're doing 1 meter, for e to the pi x dx. Then we'll do an antiderivative. So the antiderivative of e to the pi x, we keep the 4 out front, but it's still e to the pi x, and we just divide by whatever that coefficient is. And we can check that if we remember how to do the derivative. We take the derivative of that, we multiply by pi, we'd end up with just 4 in front instead of the 4 over pi. So that's the correct antiderivative. Then we got to plug in our points. So we plug in 1, we get 4 over pi e to the pi. We plug in 0, we get e to the 0. Remember, e to the 0 being 1, not it doesn't just go away when we plug in a 0 this time. So we end up with 4 over pi times e to the pi minus 4 over pi, or we wanted to kind of factor that out and make it look a little bit nicer. Could look something like that. And again, very nice if you want a nice mathematical perfect expression, but in engineering, we probably want to get that into a decimal, so we'll throw that into our calculator. And when we do that, we get 28.2 joules. So the key points that we learned from this lesson are basically 4 things. The first one is that work can be defined as the integral from 0 to d of f of x dx, where f of x is our force as a function of the distance. This is our start distance, and that's our end distance, if we know that. The second was you doing antiderivatives of polynomials, and again, whenever we have an integral of x to the n dx, we raise it by 1 and divide by the new power. That's something we're used to doing. The second is to do the antiderivative of sine and cosine. The antiderivative of sine is negative 1 over omega times cosine of omega x. And the antiderivative of cosine omega x is 1 over omega times sine omega x. And the third one being the antiderivative of e to the ax. So if we have e raised to a coefficient times x, then the way we get the antiderivative is to keep that coefficient on there and then divide by whatever that coefficient is. And then notice I've gone through and added plus c to all these. Just remember, if we don't have a definite interval, we could have any constant on there, because when we take the derivative of a constant, we end up with 0. So any 0 that we have added on here could be from a constant. So, but if we're doing it between 2 points, just as we did before, you do not have to worry about that plus c. And so that's how we do work.